Hello, physics students. This is lesson 3 in my discussion of rotation, and in particular, not just the fact that things rotate, but we're going to talk about causing rotation, aka, well, we'll get to that. So here's a door. All right, you got a door here. It's hinged, obviously, on one side. We're going to open it. All right, from the push side, okay. And all right, so we typically open a door the same exact way every time because we don't think about it. It just makes sense. And also because they most of the time have door handles on them. But when they don't, you could think about how do you open a door and why, right? You can push lots of ways, and lots of ways will open the door, but there are a whole bunch of ways that won't open the door. There are two cases in which you can't cause rotation. And that is, right, here's the hinge. Here's our top view of the door. And the deal is, if we were to take, I don't know, let's take a force, say, that looks like that. And then, well, I don't know, if we pushed like this, or like this, or like this, or like this, or like this, any of these ways, any of these applications of this force will open the door, but this one won't. You want to open a door and you try pushing on the hinge, that ain't going to work. All right, I don't care how hard you push. If we push like crazy on that hinge, the door is not going to open. The door will not rotate. All right, we can push in that direction. You get the idea. That won't work. Okay, there are lots of other ways that we could try to push and we would not be successful in opening the door, and those ways would all look like this. If we push like this, I don't care how hard, but you push on the end of the door, or anywhere along here, there's no way that this force produces the tendency for this object, this door, okay, to open. All right. In every other case, you can do anything. I mean, how do we open a door? Typically, of course, what we do is we push at the end, close to the end, right? And typically we push sort of, quote, straight at the door. And when we do that, this force we apply creates torque. So this I would call the tendency of a force to create rotation. Now, I don't like this definition for a specific reason, but it works for now. We're going to get back to the proper meaning. That's sort of like saying forces are what make objects move. That's not a very accurate statement. All right, and this is not accurate, but at least if we say create rotation, or how about this? This will work better. Or to change rate of rotation. Because you can imagine imagine a turntable that's spinning on a really low friction axle. Well, if you get that thing spinning and then leave it alone, it'll keep spinning. All right, in the exact same way that air hockey puck on an air hockey table, if you give it a little nudge and then stop pushing, it just keeps going. Its own inertia will keep it going. All right, a spinning object has inertia also, rotational inertia, and so if there's a torque, what that can do is change rate of rotation, right? Which gets at the idea of angular acceleration. So I'll even put that down now. Now we can get to the real definition. So torque is a tendency of a force to create angular acceleration. Much in the same way that a force, a regular old force, can cause linear acceleration or translational acceleration. Torques can create angular acceleration. Okay, so There are simple expressions for sure for torque. I'm going to try to show you a little bit of deeper meaning with that, the typical classic expression for how much torque a force produces. And so let's take a case where we've got this red thing that's hinged at one end. That's a frictionless axle, and maybe we're looking at a top view here, and there's a force applied here, and this here I'm going to call, this place has a special name. This place is called the point of application of force F. The place where force F acts. Because whether or not you know it, most of our discussion of physics so far, we've never talked about the fact that we could push on an object in one place on the object as opposed to a different place on the object. All we've said is we can push on a thing. Now we can say I can push here or I can push there, and those effects of where we push have big differences. We've treated every object so far. When we've drawn free body diagrams, we say, look, here's the object. And there are forces like this and like this and like that and like this, and they act on the object, sort of end of story. Now what we're saying is objects have shape and size, and we can push or pull in different places. And the location at which we apply a force has a big impact on what this object will do. All right, and this place, called the point of application of the force F, is located somewhere relative to the axis of rotation. And it's located via this vector r. That vector r is a vector from axis of rotation to point of application, oh boy, that says application, of force F. I really recommend you you should absolutely know that definition. The definition of R is super important. Okay? Now, how much torque does force F produce? Well, force F does produce torque because that force exerted at that location can cause this object to angularly accelerate, can cause this object to, if we want to put it in real simple terms, to rotate. Okay? But here's the deal. There's only part of this force that causes rotation, or that causes the tendency to angularly accelerate. And the part of that force looks like this. There is a component of F that's perpendicular to R. Only F perp to vector R creates torque. Super important. And your ability to draw a component of a force that's perpendicular to a vector R is important. And for that matter, your ability and your willingness to draw a vector R is really important. That's something that a lot of people overlook doing as a practice, but drawing those vectors, drawing R vectors, is a real good way to figure out if a force produces torque or not. All right, if you can draw a vector R, if you can draw a component of a force that's perpendicular to vector R, then there is a torque created, right? Here's perpendicular. And by definition, the amount of torque, that's a fancy Greek tau. It's like a capital T, except it's curved at the bottom and curved at the top. That's a tau for torque. That torque is R F perp, the product of those two magnitudes. So R is a number of meters. F perp is a number of newtons. This is going to be measured in meter newtons, newton meters, whichever you like. You hear a truck adds, this is a 900 foot-pounds of torque instead of, well, that would be foot-pounds, distance times force, okay? We'll measure our torques in newton meters. Now, in this case, I want you to notice there's an angle that I'll call theta between these two vectors. Here's theta. All right, F perp in this case is going to be F sine theta. Okay, so in this case, we would have that the torque is RF sine theta. All right, you usually see this form of an expression for how much torque a force creates. All right, I prefer personally to think about it like this because I'm trying to make sure I find a component of force perpendicular to r. And sometimes based on what angle is given in a problem, you might not use sine. You just have to make sure you use the appropriate trigonometric function to find the component of force perpendicular to r. Okay? Okay, now, let's take the same diagram and I want to show you something different. All right, same diagram. This force produces torque. Now before, what we did was we said it's not all of F that produces torque at distance r from the hinge, it's only F perp. What we can also do, it's the same thing as if we do this and we say this is what I'm going to call, or we can call is that straight? Hang on, I'm a stickler for the right kind of diagram. So what I've drawn here has a name. It's called the line of action of force F. All right? And here's the deal. This force F acting at this whole distance r well, the torque produced by F, like we said, is only really produced by the part of F that's perpendicular to r. Well, that's the same thing as saying that's like, what if F didn't act here, but acted here? And in particular, the reason I say here is because there's this component of r that's perpendicular to F. So here's the whole force F. And F produces, that entire force F produces torque, but only at an effective distance of r perpendicular. And r perpendicular, r perp here is called either the lever arm or the moment arm. So while the whole force F doesn't produce a torque at this whole distance r, the component of F that's perpendicular to r does produce torque. That's the same thing as saying the whole force does produce torque, but not at this whole distance, not at this whole distance r, only at this distance r perp. So this torque we can also express as r perp times F. Notice here we said r times F perp. Here we're saying r perp times F. The whole force, but only part of the vector r, as opposed to the whole r, but only part of the vector F. And guess what? If this is the same angle theta that we said before, here we said it was up here, but now that's the same angle. Notice, here's r perp, and r perp is r sine theta. So if we rewrite our torque statement, we get r sine theta times F, which is the same thing as r F sine theta. The order in which we multiply things doesn't matter. So effectively what you're doing is, if you take the whole force and the whole r and multiply by the sine of the angle between the two vectors, well, that's how much torque a force will produce. Okay? So it's just kind of neat, in my opinion, to think about, well, it's only like part of the force produces the torque at the full distance r. Or it's like saying, well, the whole force does produce torque, but only at part of the distance. All right, and those two expressions are the same thing. Again, I really prefer to think about it in one of these two ways. I'm looking for r perp times the whole force, or I'm looking for the whole r times f perp. But they give you the same answer. They give you the same result. All right. There are also cases in which it makes, in my opinion, more sense to use one approach or the other. All right, and I'll walk you through a couple of those. So here's one. This is like a board or something like that. Here's a pole, right? And then here's a plank, and then the plank is like maybe anchored here at this end, but there's a wire attached to it that looks like that. Okay. So if we say here's the plank, and here's this tension force T, we want to know how much torque this force produces. Well, now it's, yeah, look, about an axis located at the wall. So relative to here, we're saying there's an axis. Sometimes I'll do that. I'll do a circle with I'll say that's the place I'm calling my axis. I've just defined a vector r. Vector r by definition goes from axis of rotation to point of application of force. Okay? And then let's call this an angle theta because I said so. All right, well, here is a part of tension T that creates torque, T perp. All right, why am I breaking T perp into components? In my opinion, because, you know, if we stick to a pretty standard set of axes like that, R is on axis. R is along the x-axis. T isn't. So break T into components, right? We get this nice right angle between our two vectors, and then the torque. In this case, I'm going to write as RF perp. That's going to be R times F sine of theta, because T perp we could say is across from the, all right, so there's RF sine theta. And we'd probably say, you know, if this, whatever length this thing has, L, well, that's the same size as vector R. So our torque here would be L F sine theta, and then you plug in whatever you want. I don't care about the number. I care about getting to the expression. Okay, so here's a case where we break T into components. Again, in my opinion, because T is off axis. All right, T points this way, so here's a component of T that's perpendicular to vector R. Here's a different situation in which we have a domino, and there's a force F that's applied right here to the top, and this thing's just about to, we're going to start to tip it over. All right, well, when this domino starts to tip over, it's going to start to rotate about that point. Yeah? You can imagine the thing starting to do this, lifting up, but having that bottom right corner stay you know, pinned to the ground. So, by definition, our vector R goes from axis of rotation to point of, oh boy, to point of application of force. That's not too bad, actually. Right, so there's a vector R. Yeah, fine. There's a vector R. Well, what we could do, don't draw. We could say, here's F perp. How long is that? We got to make sure we're going parallel and perp. Okay, you could do that. There's nothing wrong with that. It's totally correct. But what's, in my opinion, nice to do here is, since R is off axis, and what I mean by that is if we stick to a traditional sort of XY axis coordinate system, here we can look at the line of action of F and say this is a lot like if F acted here at this distance R perp, where R perp is probably in, I mean, you know, now all we need to know is how tall is the domino. All right, so if this domino has a height h, then the torque produced by this force is, I don't know, how about h times F? And we don't have to worry about anything with angles or any of that crap at all. All right, so again, in this case, since R was off axis, it makes sense to me to try to break R into components. And it might be difficult to do in a drawing. I have the luxury here of, with technology being able to physically move this force, this picture of a force around. Sorry. But it's nice to be able to imagine, having the thing act here or here, anywhere along its line of action is the same thing. And the nice thing is when I stop here, I get this right angle between F and a component of R. Okay? So, to review, oh yeah, okay, sorry, not to review yet. Let's do a little torque ranking exercise, but maybe let's review a touch, okay? Forces can produce the tendency for objects to, well, I guess you could say rotate. The right answer is to accelerate angularly, to change their rate of rotation, all right? And that tendency is called torque. And how much torque a force produces depends on a couple of things. How hard do you push, and where do you push? And not only that, but what direction do you push? The farther away from an axis of rotation that you push, the more tendency you have to change an object's rate of rotation. The harder you push, the more tendency you have to cause a change in rate of rotation. But the more perpendicular you can push relative to vector r, that means sine of theta, well, theta approaches 90, and the sine of theta, the sine of 90 degrees is 1. The most torque you can produce is when r and f are perpendicular. Okay? All right. Also, sometimes it makes sense to break f into components. Sometimes it makes sense to break r into components. You've got to get some practices to, when each will be more convenient. In my opinion, whichever one's off axis, r or f, break that one into components. Here, t was off axis, break it up. Here, r is off axis, break it up. Okay? Here's a nice little exercise about ranking the amount of torque that forces produce. Okay? And so we've got 3 different forces that can be applied in 3 different places. This is a disk that rotates about that point, an axis that passes through A. All right, so F1 and F2 and F3, and it looks to me like I've chosen to say that F3 is twice as big as F1, and it's twice as big as F2, which means F1 and F2 are the same size. All right, we also have that the location of B is 1/3 the distance away as the location of C, as measured relative to A. Okay, so here's what we can do. We can, let's see, there's 3 different forces and 3 different locations at which those forces can act. That leads us to lots, 9, I guess, combinations of force and location. All right, so let's rank them from most to least torque. Now, a lot of them are easy, because if we apply any of these forces at location, at location A, well then the distance from the axis of rotation, which is at A, to the point of application of the force, which is at A, that distance is 0. So that means that any force, so F1 at A, F2 at A, those are ats, F3 at A, torque is 0. You can push as hard as you want at the place where something rotates. That is not going to cause a tendency for the object to change its rate of rotation. And, all right, so I'll say all of these, R is 0. It's also true that F1 at B and F1 at C, the torque is 0. Because if we put, let's say, F1 here, and here's an R to F1, well, there is no component of F1 that's perpendicular to R. All right, so I'll say F1 perp is 0. So there's 5 of our 9 combos produce no torque at all. All right, so let's see. What we're left with, I'm going to write them down. Don't write them down yet. We got, let's see, F2 at B. We got F2 at C at. We got F3 at B. And we have F3 at C. So, biggest and smallest. Well, I hate saying this, but it should be hopefully clear that F3 at C is the biggest. Why is that? Because we get the most force at the biggest distance. And we can actually express the torque, right? We could say that this torque is F3 times R. That's a R. Okay? The smallest one is going to be the smallest force at the smallest distance, and that's F2 at B. And we can express that torque. Let's see, that torque is, well, all right, F2 at R over 3. And check this out. We know that F3, oh boy, F3 is twice as big as F2, so we can actually write this as 2F2 times R. So here we get a third of FR, here we get 2FR. All right, now these other ones, let's express the size of F3 at B. All right, well that's going to be the torque equals F3 R over 3. Remember, that's 2 F2 R over 3. Okay, F2 at C, F2 is, well, let's see, forget that, sorry, arrow. This torque is going to be F2 at a full R. All right, well, check it out. This one is a third of F2R. This one's 2/3 of F2R. This one's a full F2R. This one's 2F2R. So we have our correct ranking. All right, and that ranking is that that this guy, let's take this, yep, goes here, and this guy goes here, and then we're done. Okay? So being able to relate distances to each other and forces to each other, and then to be able to write legitimate statements for torque in terms of the same common factors is a great way to be able to rank the amount of torque that these things produce. 1, 2, 3, 4, all the same amount, which is 0. Okay? Okay, folks, we will get into soon writing net torque statements. When there are multiple torques acting on an object, multiple forces acting on an object that produce torques, how do we write a net torque statement? All right, a lot like writing a net force statement for an object that we only consider a point. Now we talk about where forces act and what direction they act, and therefore what torques, how torques combine, and what the result of that is. Okay, so that's coming up. Thank you. Adios, and fairly well.